Okay, let's go ahead and get started. Hello, everyone. I'm Charlie Smith, Principal Consultant with ESIG, and I also serve in a leadership role with the Global Power System Transformation Consortium, or G-PST, whose mission is to bring together key actors across the globe to catalyze a rapid clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. At the core of the G-PST is a large cross-section of system operators from around the world who are dealing with a rapid transition from a system based on synchronous machines to one built around inverter-based resources. The 5 pillars of the consortium include research and peer learning, technical support, workforce development, standardization, and open data and tools. ESIG is the co-lead on Pillar 1, along with Mark O'Malley of Imperial College, and more information on the G-PST can be found at globalpst.org. As the co-lead on Pillar 1, ESIG would like to welcome you to the September monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is in addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both system operators as well as members of industry and the research community. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I would like to go over a few logistical matters before we get started. First of all, lines will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we will use the Slido platform at slido.com. To ask a question, please navigate to slido.com and enter ESIG 11 as the event code. The instructions are also at the bottom of this screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Today's topic is on a practical field guide to the diagnosis and mitigation of oscillations in IBR-dominant power systems. As you might imagine, with the changing nature of the resource mix and the retirement of conventional synchronous machines with their inherent physical properties like inertia and fault current contribution, this is a topic of increasing interest and importance to the industry. A number of systems with increasing levels of IBR are beginning to experience system oscillations that they have never seen before. At its March Spring Technical Workshop in Tucson this year, ESIG co-sponsored a one-day workshop with G-PST on system oscillations, taking a deeper look at the monitoring, tracing, and mitigation. At the workshop, Nick Miller gave a preview of a field guide to system oscillations, which he has been working on with us for nearly 2 years, along with a small group of other people. It's been a while coming, but it's finally here. We promised to share it with everyone once it arrived, and now that it's been released, we're pleased to share it with the community at large. The webinar will introduce this practical guide as a starting point for practitioners who encounter oscillatory behavior and want some diagnostic assistance. It will be presented by Nick Miller, an internationally known power systems engineering consultant, who likes to point out that he spent 3/8 of a century with GE. Nick has a list of credentials as long as my arm, and I won't go through them all here, except to say that he is a good friend and a lifetime member of ESIG. I greatly value his leadership and contributions to the industry, and I look forward to hearing what Nick has to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG 11 to ask your questions. Let's go ahead and get started. Nick, I will now turn it over to you.
Alrighty, thanks, Charlie. It's, as always, pleasure to be talking to this august group. And as Charlie says, this has been a long time coming. So, and it's quite a document. So today will necessarily be brief overview, and we hope you'll use it and come back to us with questions above and beyond today. So with that. This is a shot from the cover, and a couple of people have given me grief for the artist putting the wind turbines too close to shore, but I had a little fun painting this anyway. So first and foremost, this is what the cover of the document looks like. You see a link down at the bottom. It's easily found on the ESIG website. Many of you probably have seen this link because that might have sent you to this webinar. And before I go any further, I want to acknowledge that this is while I herded the cats and I did a great deal of the writing, there was a long list of contributors that are on the right here that I greatly appreciate. Some people put a great deal of effort in, but everybody made a useful contribution. And while I'm at it, I'd like to particularly call out my technical editor and general aide in getting this thing across the finish line, Karen Matchett, who kept me honest, fixed countless tortured syntax and nonsensical things that I'd written, and she did yeoman's job to get this thing done. I hope you appreciate how nicely polished the document is. That's partly my doing, but a lot of color. So thanks to everybody on the list here. I will not try to read it off. And again, and thanks also to Julia, who did extra duty as an editor and a reviewer of this. So you have seen one or two of these slides, some of you when I introduced this earlier. As Charlie said, this is the genesis of this document is from the G-PST founding system operators who have gotten feedback and experience that system oscillations are becoming a problem. So the work spec for this document was help. We need help with oscillations. With feedback from members of the stability task force and others, we spent quite a bit of time wrestling over what would be a valuable contribution, and that's really where this the emphasis here on a practical guide. There's a great deal of complete and in-depth material out there. There are technical papers. There's some beautiful documents by Seagray, by IEEE, contributions from many of the co-authors of this document that are deeper dives. The point of this document is to fill what was perceived by me and others as a gap, as a starting point. So the idea here is a practitioner, the person in the system operating room or possibly in planning that gets us oscillography or gets simulation results that have oscillations in them and says, somebody says, it's your job to figure out what this is and what we need to do about it. Do we need to worry about it? What's happening? Do we need to fix it? How can we fix it? And the idea that the user needs a little bit of help in starting down a road towards diagnosis and mitigation is the driver for this. So this document can't be all things to all people. It would be an encyclopedia, and that's not what it is. And indeed, I use this diagram here when I've been explaining this to some of you who are on the call and probably heard me speak earlier. This is the first aid guide. The patient's bleeding. What do we do? So it's only 140 pages. You could argue that that's long or that it's short. It's both, quite honestly. But it is a place to start. It is meant to be reasonably comprehensive, covering a spectrum of credible and experienced sources of oscillations in power systems, particularly those with high levels of inverter-based resources. It's not this thing on the right. It's not a library. And the references at the end are surgically selected to help the reader go further into use. So if you want to vision yourself as a crusty old diagnostician like House on the right, you're in the right state of mind for this document. As is always necessary, we're addressing a spectrum of users, and as always, an executive summary is a good thing. So I used this slide last time we spoke. Somebody will remember it. And there's a short executive summary, a few pages, that kind of set the stage, and importantly set the stage for what's in the guide, and that is, if you observe oscillations in the system, there are a couple of short likely causes. So Occam's razor is always the simplest explanation, is probably the right one, in case you didn't recognize Occam's razor. And to that end, this is a little bit editorial, but is based on lots of experience, not just my own. We have sort of three things are likely if you observe oscillations. And the first one is that something's busted. That is that something is not what you thought it was. So the device isn't been installed the way you think it should be. Something is malfunctioned. Something is wrong in your model that is not representative of what's going on. These things can be anywhere from reverse polarity on sensors, or a tooth is broken, or you've used the wrong model, but something isn't right. This is an important first point, because there is a population, including many people that are on this call, that are biased towards doing simulations, as I am. I spent my whole life doing simulations. But many causes of oscillations don't particularly lend themselves, particularly at the diagnostic stage, to doing simulations. If you don't know what's going on out there, if you don't have a good representation or good understanding of the physical reality, then simulations will not take you very far. Simulation can be highly useful for zeroing in and identifying, proving causality and proving and evaluating mitigation. But for the initial diagnosis, what's wrong with the patient, not so much. The next thing is one that is a single statement. So each one of these statements are very short, and practitioners on the call will recognize that there's a world of information behind each of these simple clauses. Something that is a recurring theme throughout the industry is that the controls on the devices, and we are mostly concerned here about IBRs, but this is a world that has a mix of inverter-based resources and synchronous resources and other stuff. We haven't gone to 100% IBR necessarily world, but the introduction of inverter-based resources opens a spectrum of potential pathologies, because these resources have the possibility of acting very fast and very aggressively. And in some cases, they're being asked to do so in a fashion that will cause oscillations. So this second line item here covers a world of pathologies in a short line. You're trying too hard and you're driving the system unstable. And then finally, in this world of observations, the line between what you see in the system and what's being simulated gets muddy, and I'll talk about that a little bit more. But simulations themselves can produce oscillations that are not necessarily reflective of what's going on in reality now or in the future. So there's a bit of overlap between observed in the field and observed in simulation. And there's lots of ways that simulations could go awry, and there's a fair amount of attention given to that into this report. So there's these three sort of basic elements of Occam's razor, and yes, not everything fits neatly into these buckets, and each of these buckets are in fact quite complicated. But the idea that as soon as you see an oscillation, it's an exotica is not a practical approach. And that is driven home repeatedly through the course of the document. So sorry about this slide, but I needed to talk from it briefly. This is a condensed version of the table of contents. It's an eye chart, but the rest of the talk here, I'm going to go through some of the high points of this. But I wanted this just in case these things that I can't touch on in the space of 45 minutes. There is a lengthy hierarchy in this document that is aimed at a spectrum of different kinds of readers. And you see that a little bit in this table of contents. So I got this executive summary, it's only 3 pages. Even the faint of heart can wade through 3 pages and get a sense of what's up. Then there's an introduction explaining to you what this document is and isn't. Hopefully I've captured that at a high level here, but there's more to it, and some instructions on how to use the guide. All right, that's kind of for everybody. Then there's a fair amount of tutorial information that is quite basic, that's talking about system stability. Oscillations are a subset of system stability. I will come back to some of the taxonomy and choices that we made for this document. The point here is that we have sort of set the stage with some thoughtful, but hopefully not overwhelming discussion of system stability. So those of you that are on the call trying to figure out what this is about, but are not charged with fix this problem, will find these earlier sections of the document hopefully illuminating and help you get grounded in before you go into what is frankly pretty gory details. And one person's gory details, another person's too shallow. We're going to see that repeatedly through this. Then as the document goes further on, there's a few topical discussions, and then we dive into how a framework for diagnosing what's wrong that is, again, returns often to the sort of medical imagery of the diagnostician, collecting symptoms and trying to figure out what it might be and framing tests for what is causing the illness and what might fix it. And that goes on at some length. There are a couple of layers in this document, which I'll talk about quickly, that address specifically risks and pathologies that are associated specifically with simulation. So there's a little bit of a dichotomy here. When you get oscillography from a field device that says something that is oscillating, you got a pretty good chance of being sure that it's quote unquote real. You might not know what it is. Presumably you're using this document because you don't know what it is, but it's something real. Whereas oscillations in simulation, one of the very first questions is, do I believe the simulation? And there's some overlap. So there's quite a bit of discussion of that. And then finally, we have some closure. So far, sorry for the eye chart, but the other thing is for the reader, this is a greatly reduced table of contents from what's actually in the page, in the document. We made a decision, an editorial decision. The table of contents is several pages long and goes down multiple layers in the organizational hierarchy so that the user can pick the thing up and say, I know there's a section on subsynchronous torsional interaction, where is it? I know there's a section on ferroresonance, where is it? I know there's a section on FFTs, where is it? So the table of contents is kind of daunting, but it is meant to be subsequently usable for somebody that's got this on their desk. So Nick's vision of the future is that you have a hard copy of this thing, it gets pulled off the shelf, it gets dog-eared, it has coffee stains, it has your marginal scribbles on the corner along the pages saying, I saw this, this is crazy. We're hoping very much that this becomes a working document that gets used as you go forward. So with that, we propose within the document, and a good portion of the layout of how to use it follows this high-level flowchart. And I'll walk you through this quickly, and then we'll dive into a few of the pieces as we go along. The idea here up top is that you're starting with observations, field measurements, oscillography that says I've got oscillations. Or you've got simulations that show oscillations. And you see that they're segmented. When we started to write this guide, it was the original intent was sort of only for field observations, but the diagnostic process between what's going on in the field and what's going on in your simulation has so much commonality, and there's so much commonality of deep dive diagnosis that includes simulations that these two are different, end up being different faces of the same coin, or at least cousins. But when you have planning simulations, when you have simulations that show up oscillations, you're looking presumably in the future or some condition that maybe you haven't operated at, and you see oscillations, there's a question, do I believe the simulation before you start diving into what's wrong? And there's a fair amount of help for the reader to avoid wasting time on chasing will-o'-the-wisp, things that are commonly amiss and mistakes that can be made in the course of making simulations in the narrow context of causing oscillations. This is not a guide for all things simulations, how to do all kinds of simulations. This is about oscillations. So once we get through that, there's, okay, I believe I've got oscillations. What might it be? And we have a stage here, which we've called an initial assessment. The initial assessment asks dozens of questions and looks for symptoms the way a medical diagnostician would go, and so comes back hopefully with, oh, it might be this, and hopefully you have one or two possible ailments. Again, I keep using that language because it fits rather well with the process, at which point we go deeper into a specific ailment and start looking for how it manifests itself, how one designs tests, what tools are best suited to determining causality and evaluating mitigation. And in the course of doing that, there's an expectation often that simulations will be done that are diagnostic. It's like, okay, I saw this, I'm going to set up a model. Do I trust the model? So there's some overlap between those two orange boxes that are different colored because they're specific to simulation. And finally, we come out of detailed assessment with one or two paths, one of which is, here are some actions you can take. Those could cover a fair spectrum from operational to changes in controls, to actual changes in physical. And okay, so we'll get into that. Or not everything fits in this guide, and you may very well have a problem that is so complex or so new that we can't help you. So this is not the end of the process. Now, this is a little maybe a little tough to stomach. As I said repeatedly, oscillations are one manifestation of poor stability. The industry and many practitioners on this call understand that stability is a broad topic, of which oscillations are a subset. you'll recognize this IEEE figure, which somehow when I made the chart here, I cut off the source. IEEE gets the credit for this. I have to be careful about that. We were very careful in the document to give credit to all the figures contributed by many. But in the end, this IEEE hierarchy isn't as useful for diagnosis of oscillations as you would like, because the behaviors tend to often cut across multiple of these boxes. And in the end, the hierarchy the taxonomy and hierarchy that we've adopted in this document are the 5 major categories listed at the right: subsynchronous and supersynchronous phenomena, voltage-related problems, uh, uh, transient stability, angle and transient stability related problems, frequency control related problems, and harmonics. And you'll see that as a recurring theme, and I'll get into some of the details at a high level today. So that's what to be looking for as you go in. I'll be quick going through some of these points, but I put them in the presentation today to sort of give you consciousness raising. From a practical point of view, again, and that's the driving gestalt of this document, is practicality. There is sort of 2 flavors of oscillations, and if you read the literature, sometimes it seems like the decision is sort of Boolean. Is the oscillation forced, or is it a natural oscillation? And that's pretty commonly used language. So forced oscillation, sort of in the cartoon version, is something is driving the system at in an oscillatory fashion. In the field, this manifests itself, for example, as something in limit cycles, banging on and off, on, off, on, off, on, off at some frequency that stimulates the whole system and may indeed be driving it unstable. Those forced oscillations frequently manifest themselves as observed oscillations with 0 damping, neither growing nor damping out, but specific to some operating condition or some condition that causes something to go wacko. And that is frequently of the first flavor of the executive summary. Something's busted. But the conditions that may drive forced oscillations may come and go, and there's some examples of that, and examples in the guide as to how you can spot forced oscillations from oscillography and separate them from natural oscillations. So natural oscillations on the other end of the spectrum are those of us that are more mathematically inclined think of as negatively damped eigenvalues. So we love doing root locus and all sorts of good stuff like that. And the eigenvalue has migrated into the right-hand plane, and it is naturally unstable and will spontaneously result in oscillations. Those are real things. But the reality is that systems frequently are a mix of these 2. And I'm not going to walk you through every one of these arrows, but there's a lengthy discussion that's mostly by me. I'd be interested to hear whether people agree with me, but it's drawn out of the very good IEEE documents, for example, by the forced oscillation group that was Dan Trudnowski and others. There's some great stuff in that. But the idea here that there really is a spectrum, and right in the middle can be devilish, where the system has a poorly damped eigenvalue that is being stimulated by something that's busted. And that makes the diagnosis and mitigation, particularly the diagnosis of causality, can be really tricky when you're in the middle of poorly damped but driven. And there's examples throughout the document for this, and it's kind of important practical nuance. So that returns. The next major discussion, and it goes on for many pages, and I'll talk a little bit about it, are all the different analytical tools that can be brought to bear for for not only diagnosis of causality, but design and mitigation. These 9 bullets here, 8 bullets here are sections within the document where we talk about state space, etc. Those of you on the call that are practitioners will recognize, wow, you know, you can have a whole textbook on state space methods. You can have, you know, there's massive publications and ever growing on dynamic model frequency scans. We talk about those, how they can be used, lots of references. So I'll get a next couple slides are just maybe a few things I pulled out of the document. I don't need to spend a lot of time on them. There's figures and some discussion of when and where these tools can be useful. So this is this is a nice figure from Shahil that's showing a natural frequency pulled out of a dynamic frequency scan at around 17 hertz, and that becomes a very useful tool for diagnosis and for design and mitigation. So this is really powerful, and it's very powerful for phenomena that may not be phasor domain applicable. There's a fair amount of discussion about ways to slice and dice and extract useful information from field measurements. So you get some oscillography, things like FFT, what makes a good FFT, how you can present that. So this is a nice figure from NREL of some oscillations that are around 18 hertz, but actually are changing over the course of an hour. So a drift in the frequency and a change in the amplitude. These could be really useful for trying to understand sensitivities and to ferret out what's really going on from field measurements. This is a different example. This is from a nice CalISO paper. This is a figure that's out of a paper from some of the tools that are present in the CalISO operating system that are starting to show up in other systems. There's something similar at ISO New England, and these showing up around where EMS systems collect information out of PMUs. There's a really nice example in the document from CalISO where this system sensed a system oscillation on COI and was able to point to bad actors in Southern California. So these tools are very useful for finding the bad actor. Bad actors especially are of concern when you're on the left end of that natural to organic frequency spinning. So there's some discussion of those. There's a few experts made contributions to the document. So in the end, this is the first of 2 eye charts. You folks saw these earlier when I presented. There's an applicability matrix. So across the top are 5 major categories of disease, and under that are 15 subcategories. And then down the y-axis are groups of different kinds of tools, state space tools, tools that are based on network impedances, tools for locating faults, etc. And the idea here is that the color coding says dark green, this is a tool that is one of your core analytical tools for handling this particular ailment. Light green is you might be using this tool to augment results and diagnosis that comes from the dark green tools or under some special circumstances. Yellow means this is a tool to be used with a great deal of care and may be inapplicable to the phenomena there, so don't be greatly cautious. Gray is it's irrelevant. This is not the right tool, and it doesn't make any sense to be using it for this particular variety. And red is counterindicated. Okay, you don't use these tools for that particular phenomena. It's invalid. As is always the case with these kinds of things, there will be people that don't quite agree with the grading. Interested to hear from you, and there's a fair amount of discussion in the document to try to capture some of the nuances that can't be caught in a chart like that. There are, so then going into that box on, do you trust your simulation? These 3 bullets here are subset from the table of contents on what's in the simulation credibility. So there's a bunch of questions and other kinds of things that are designed to help the user the sanity check their work. It's like, is this an artifact? And there's lots of different kinds of artifacts in the list. I'm not going to read the questions here, but they go on for several pages of ways. And if you flunk these tests, then there's a much deeper discussion of what to do about it at the towards the end of the document. That's called simulation failures. So we tried to capture. There's a lot of practical words in there, inputs from people that have made their livings doing simulations, and bits of advice of, don't make this mistake, don't do this, avoid doing this, make sure you do this, that you won't find, frankly, in more scholarly works. So again, emphasis on practical. Then we get into this initial screening that I told. So again, we introduced this chart before. This is obviously a killer eye chart, and it will get lots of people excited. Some people are going to love this, some people are going to hate it, but this is the reality, again, like medical diagnostics. You get a whole bunch of symptoms, and the left column is answers to questions that have been posed for the user, looking at the oscillations that they see. Are they sawtooths? How fast are they? Are they damp? What's involved? What's the participation? And lots of dark green in the columns, which are the different diseases, will point you in a direction of saying this is likely. Again, if you observe something and it's red, it's not that phenomena. So those are mutually exclusive. And some of them are not meaningful. So this is a lot. Whenever you make a condensation like this, you throw away a lot of nuance, but this is a nice, and some people have been very enthused about it, tool for trying to point you in the right direction. The idea coming out of this is that you go into this detailed assessment here, and you come in with, okay, I've seen a whole bunch of different things that make me think this is subsynchronous torsional interaction. Do I have enough information? Can I extract the information I need from the signals I've got? Can I do signal processing? Do I have the right FFTs? Can I do, or do I need to go back and get more field measurements? Or do I move on to start setting up simulations to do causality? And there's lots of tests lined up that are aligned with the different kinds of diseases that are run these kinds of tests, look for these kinds of things. And then some questions: do you really believe? Have you determined with a reasonable amount of confidence that this really is the cause of the oscillations? And then this next point is rather important, and several of my contributors made a big deal out of this. It's like, once you've figured out that there's an oscillation out there, do I really need to do anything about it? All right. It's like, there's a certain degree of triage in a real power system, in a practical power system. Nah, this oscillation is not worth pursuing, is a perfectly legitimate conclusion. Now, there's a lot of discussion up front and back and forth. Nick's view of the world is that you have to be reasonably confident that you understand what's causing an oscillation, even a seemingly minor one, before you decide to ignore it. That's why it resides here rather than upstream. Now, some kinds of things maybe you can dismiss right up front, but you got to be very careful. Then we go into countermeasure design. There's a fair amount of discussion of different kinds. So this is the overall flow. Each of the discussions within the detailed process kind of follow that. Now, there's a couple of deep dives. I won't spend much time on this, but there's a latency, communication latency, cuts across causality in several places. So there's a lengthy discussion about the constituents of latency and how they can bite you and what you might be able to do about it. And then I'm just going to give one sample out of each of the 5 sections here very quickly, because I'm not only because I'm running out of time, but it doesn't make sense to dive in. Under the subsynchronous and supersynchronous oscillation, there's 5 flavors. There's these kind of cool drawings. I thought they were cool. Not everybody likes them. That are designed to sort of point out, okay, for SSTI, we are specifically talking about interaction between the inverters and the torsional reality of synchronous generation. There's a whole section on language because the language of subsynchronous behavior is not completely uniform. There's 14 flavors of subsynchronous stuff in the Segre taxonomy. There's a different number in the IEEE taxonomy. I tried where we could to avoid using acronyms because we don't have a great deal of we don't have perfect consistency. So these drawings are meant to say, this is the interaction we're talking about. So this is, for example, the red is old school HVDC subsynchronous torsional action between a single big IBR. The blue are different flavors between modern IBRs and maybe a multiplicity of them. So there's lengthy discussion about what they look like, what to look for. The next major family is voltage control induced oscillations. There's 3 subsets that are left on the left that are in the discussion, different kinds of malbehavior. This kind of cool example is courtesy of Ling Ling Fan, a cool system that is stable until it gets too stressed, and then the voltage control goes unstable, driven by, primarily aggravated by communication latency. So it's kind of a cool example. Transient synchronization, I like this example because we've got some swings here that look like nice 1 Hertz swings, but they don't actually lend themselves to analysis with eigenvalues. It's actually very nonlinear behavior of a system that is near the point of transient voltage collapse manifesting itself in oscillations. And there's a bunch of kind of good discussion on that. Then we talk about frequencies, and you have different kinds of things. This is a cartoon that I made to kind of drive home. There's a whole discussion on inter-regional power oscillations that tend to be dominated by active power control. They could be exacerbated by secondary controls, even tertiary controls. And in a complicated system, you get a multiplicity of mode shapes, so that mitigation can be really tricky where you can squash one mode and exacerbate a different mode, or the mode shapes can shift by different operating conditions. There's a fair amount of discussion of that class. These things are pretty well analyzed, for example, by phasor analysis. But the modeling can be quite tricky because it can spill into regimes where the bandwidth of the plant models is inadequate. There's a whole discussion on harmonics that are somewhat separate. You could argue that they shouldn't be here, but harmonics manifest themselves as oscillations. And in this world of very fast inverters, high frequency pulse width modulation, the line between traditional harmonics and very fast control interactions are quite a bit blurrier than they might have been in the past. There's some guidance on how to set up simulation diagnostics. There's a flow chart here with a bunch of help for the thing. Then I talked again back into the simulation credibility. We now get into failures. I won't go through, but the list on the left is again taken from the table of contents. Different modes of ways to check that your simulation is credible. There's a whole long talk about single machine infinite bus tests, things that work, things that don't, ways to avoid numerical instabilities and other kinds of artifacts that may present themselves as oscillations but are bogus. Okay, and then we get to the end here. So there's a closure. Put quite a bit of effort into the references. The references go on for several pages, but they aren't thousands of references. We could easily, this is a very rich topic, could easily have had thousands of references. Tried to segregate the references by the general pathologies. We tried to get the best ones. Be interested to get some feedback. People coming back and saying, oh, Nick, you missed this reference, which is a gold mine. Those kinds of feedback are most welcome. As I said, this is the first cut. Pretty excited about it. I think that the industry, that it's filling a gap that the industry needed help with, and it'll be interesting to see how it's received. If it's successful, then people are going to have a whole lot to say about it. You missed this. I don't believe what you said here. You should have asked this question as well. Those kinds of feedbacks are most welcome, and hopefully this thing will be just Rev 1. There's a glossary that is that's the usual acronyms, except that I added an annotated column. Those are Nick's view of what these things really mean. You might enjoy it, you might hate me for it. And then finally, we're wrestling a little bit right now. My vision, as I keep saying, is that for people to have hard copy with coffee stains on it, we're not exactly sure how we're going to get hard copy into the hands of users. The simplest thing is for you to download it and print it on your company printer, but it's 144 pages and it's got high quality graphics in it. You don't want to print it on your inkjet because you're going to lose, right? It wants to be printed on good paper with a good printer. Okay, I will stop there. I think I got right on time. Sorry for the whirlwind, folks. There's a lot in here, and let's take some questions.
Okay, thank you, Nick. And the questions we have, I see 23 questions in the Slido. So let's just take a look at the ones that have risen to the top and try to go through them in order. So one that's got a lot of thumbs up is, what are forced oscillations? How are they different from natural oscillations in the context of damping?
Okay, good question. And the first part of the answer is please go read the document because it's a couple of pages long. But forced oscillations are generally ones for which linear analysis and eigenanalysis are only marginally useful. Something is, I'm going to use the technical word here, is whacking the system. Okay, and it is they often manifest themselves as being driven rail to rail. That's not always the case, but that is a very common symptom of forced oscillations. So they don't care much about eigenvalues. The system is getting shaken, and you'll see there's a cool example quite recently from one of my customers that agreed to have it in there of a something wrong at a solar inverter, one string out of a plant, and the thing is sitting there going ratchet, 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 bang, ratchet, 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 bang. That's a forced oscillation, classic, and it's driving the system with zero damping. It's just sitting there doing it until the conditions that cause that particular instability go away, and then it stops. On the other end of the spectrum, natural ones very much lend themselves to linear analysis. And my favorite tool is sort of root locus. You take a system, you've got all the state values, you got an A matrix, and there's some discussion of linear, a short bit of tutorial on A matrices in the document if you don't know what I'm talking about. It's not enough to train you in linear analysis. That's a whole undergraduate course. But as you stress the system or crank up a gain or whatever, the eigenvalue starts to drift into the right-hand plane. And any sort of stimulus, and of course there's always background stimulus in the system, will cause that oscillation to grow. As soon as it crosses the real axis, it's unstable and growing. So positive damping left of the axis, you stimulate it, it will damp out. And as the damping gets better, and there's lots of criteria out there for damping, my point with that opening chart there is that in a practical system, it's not unusual to get a mix. And there's a couple of nice examples. There's one where there's a forced oscillation at 1 hertz that is stimulating a natural frequency that's actually relatively well damped at 11 hertz. And you see the system getting bang, ring down, bang, ring down, bang, ring down. That's a mix of those two phenomena. When they get close in frequency, the diagnostics get really tricky. So yeah, hope that answered the question.
Okay, we got a lot of questions here, so let's move along. Please provide comments on the oscillations due to large battery storage system integrated to a battery. I'm interpreting this as oscillations due to the battery converter with the system.
Yeah, so I have trouble making a generic answer to that. Certainly batteries have high, are IBRs. They have the possibility of having very high bandwidth controls. There is a multiplicity of pathologies that go with, for example, the voltage regulation. So those are discussed in the voltage regulation. You got gain too high, uh, the system gets too weak. So this is a recurring theme. This is line 2 of Nick's executive summary. The gain is too high for the conditions, so the control is tuned to a system normal, and it's unstable when the system is degraded. That can happen with BESS or other things. There's a cool example that came out of that Cal ISO example. I mentioned that, where the PMUs showed an oscillation on the interface between California and Oregon, and it turned out that it was being driven by 2 battery energy storage systems in Los Angeles. And Nick's practical rule: what's new? These were new installations, and something wasn't right. And they found, as soon as they went to look at those 2 battery projects, they found something amiss. And in fact, they never actually said what was missed, but I'm guessing that they had a signal polarity wrong, or they pure unitized something wrong. Those are practical things. In this guide, you won't find in a scholarly work, oh, go check the polarity of the leads, or go make sure that somebody per unitized to physical units when they implemented the control, or make sure that they didn't lose a square root of 3. Those are like, yeah, you shouldn't make that mistake, but it happens all the time. That's practical guidance. Okay, next, Charlie.
Okay, the one from Australia. In Australia, tie lines have been dropped and governors are not providing primary control. Is this unfriendly for frequency stability with mainly IBR?
Well, oscillations, certainly lack of frequency control is a bad thing. I think I could say that without hesitation. Subsystems need to have somebody in control of frequency. And, one mode of oscillatory failure is, for example, a subsystem isolating with frequency control enabled, with nothing providing isochronous frequency control. So the system drifts off and maybe can't reach a stable equilibrium. Having controls off is not something, I can't make too gross a generalization, but having controls off tends to drive monotonic, not oscillatory failures, if I were to make a wildly sweeping generalization. But yeah, you need frequency control.
Okay, a question for you. I was wondering if you had seen any forced oscillations occurring due to battery storage systems providing fast frequency response services that track frequency.
There have been anecdotes. We just completed some work for ERCOT, for example, searching for that kind of problem. One of the pressing practical and economic drivers is there's a strong economic motivation for battery energy storage systems providing primary frequency response to have much more aggressive gain, that is less droop. And on the face of it, higher gain is a risk element for driving oscillatory problems. Having said that, I'm not aware of any oscillatory failures that have been due to high gains. Now, there is a story, not a story, an actual event in South Australia, where a relatively remote battery system with a really high transient frequency response had so much pushed so many megawatts into the system that it caused separation, actually caused a relay to think that there was a separation. It caused a line to open. So, you know, high gains can manifest themselves in different kinds of pathologies, not the least of which is they can fool relays. Do those manifest as oscillations? Conceivably, but usually not. So yeah, it's a risk, but I haven't seen it.
Okay, so here's one that seems to be becoming ever more popular, Nick. How do you determine the source of oscillation when you have multiple IBR interactions?
Yeah, so that's a long answer, and so there is a whole section on on locating the bad actor, because that ends up. So, you know, again, this very good question. Somebody asked about forced versus natural. Occam's razor says that the first thing you look for is a bad actor. Something is, the technical word is wigging out, and you want to go look for that. And tools to help point you in the right direction are varied. There's these dissipating energy function techniques that have been implemented. ISO New England's used them with some considerable success. CalISO has got some of that built into that system I talked about. Those are and for some classes of bad actors, they have been very successful. The jury is still a little out, and in fact, I got pretty heated debate as an author of this about the use of those methods with IBRs. So my diplomatic answer is that appears to still be a work in progress. Nevertheless, that's one of the ways that's helpful. These, you know, using PMUs and using distributed measurements can be very helpful. One of the ways that the bad acting batteries in California were observed were these heat maps of oscillatory amplitude. So they went and they said, well, okay, this is there's megawatt swings on the tie line, but then they went and looked at voltage swings and found a hot spot of voltage swings in the vicinity of the two bad actors. So, you know, it's a little bit like medicine. You know, you start looking and say, what, you know, does this hurt? And those techniques can be very good. Then you start going into the diagnostic simulation. You start building hypotheses about what's going on. Sometimes you find that your model isn't what's going on out in the field. Sometimes you find that your model's good and you didn't test the operating condition that the oscillation occurred under. So there's a multiplicity of paths forward. There is not, and there isn't like a cookbook. There isn't like, you know, a tree. Go Boolean question. Yeah, true, false, true, false, true, false. Out pops the answer. This kind of diagnostics doesn't lend itself to that. Sorry. Okay.
Okay, I think we got time for maybe one more question, Nick. What oscillatory modes become more challenging as synchronous generation is incrementally removed from the system?
You know, certainly the whole section on subsynchronous behaviors takes on more and more weight, and it's already got a lot of weight in the document. And there's kind of a couple things going on there. So the bandwidth, you know, and I'm going to talk in generalities, the bandwidth of these IBR resources is generally greater than synchronous resources. You know, that is a two-edged sword. There's great systemic economic and societal value to the fact that these things are more agile. But they bring the risk of introducing new kinds of oscillations and new shapes, and you got to be careful. So yeah, and one of the things that we keep seeing that again fits in Nick's Occam's razor is that the fact that these controls can be very fast, it can be very aggressive, doesn't necessarily mean that they should be. And generally speaking, as the system's strength, and there's a lot of the practitioners that'll be on this call are wary of some things as simple as short circuit ratio, because that's a blunt instrument. But as the system strength drops, these progressively more aggressive controls, when they're ill considered, create a higher risk of oscillations, and more due diligence is needed. Yeah.
Okay. But we're about at the top of the hour, so we're going to need to wrap it up. I want to thank Nick for this really informative webinar on the Field Guide to System Oscillations. I think it'll really serve as a great resource for all of us. And as I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your participation, and if you'd like to stay engaged, I'd like to invite you to participate in the next ESIG webinar on September 30th on DER management and implementation use cases. I'd also like to invite you to have a look at other upcoming webinars, as well as the Fall Technical Workshop in Providence, Rhode Island in October. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Nick, I want to thank you again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks again for your participation. See you
Thanks,
soon.
Charlie, and thanks everybody. Enjoy the beastie. Yeah. Cheers.
Thanks. Bye-bye.